Hello, I'm Patrick. I will present our paper RectEuler, Visualizing Intersecting Sets Using Rectangles. Let's first dissect the name RectEuler. The first part, rect, refers to rectangles, the visual building blocks used in our visualizations. The second part, Euler, refers to Euler diagrams, a generalization of the better known Venn diagrams. Euler diagrams visualize set-type data using closed curves. Intersections of sets are represented by overlapping regions. As a motivational example, let's have a look at a set system represented as a table. It assigns characters of the TV series The Simpsons listed in the first column of the table to sets based on their attributes. Even for such a relatively simple set system with only a few sets, the tabular representation is confusing. Therefore, we need a more accessible way to represent set-type data using visualizations. We propose RectEuler, a fully automatic Euler-like visualization technique. Additionally, we introduce an interactive web-based tool to further explore our automatically generated diagrams. Euler diagrams are a ubiquitous visualization technique with a long history. Already in 1761, the Swiss mathematician Leonhard Euler used graphical representations to illustrate logical operations. Later on, John Venn introduced visual representations of sets, nowadays called Venn diagrams. In contrast to Euler diagrams, a Venn diagram always includes all possible intersections of all sets. An abstract description characterizes the relationship of sets and their intersections formally and does not specify any concrete graphical representation. Therefore, the Venn diagram on the right could be represented by, for example, circles, rectangles, or even splines. In the following, we will have a closer look at rectangular Euler diagrams. A diagram is well matched if the visualization reflects the abstract description. This diagram contains all zones present in the abstract description and no additional extra zones. Set visualization is an active field of research. Various techniques have been proposed to visualize the relation of sets and their intersections. SetNet by Rogers et al. Represents sets as circles and elements as dots. If a set is not representable by a single circle, it is duplicated. Euler diagrams drawn with ellipses area proportionally introduced by Weibo et al. Uses ellipses as geometric primitives. In contrast to our and the other related techniques, it is an area proportional method that optimizes the overlap of the individual sets based on the input data. Euler view by Simonetto et al. Is a technique to create Euler diagrams based on planar graphs. The resulting Euler diagrams are well matched. However, the diagrams have many highly concurrent curves. Recently, Wallinger et al. Introduced metrosets. Unlike the other presented methods, metroset does not use regions enclosed by intersecting curves to indicate the set intersections. Instead, they use a metromet metaphor to visualize the intersection of sets while including the elements directly in the visualization. We introduce a set of properties that the diagrams created with our method should have. Let's first consider the semantic characteristics. Euler diagrams should ideally be well matched. They should include only the zones of the abstract description and no extra zones. Like most existing techniques, our method is not able to generate visualizations fulfilling this property. Therefore, we set our main focus on including all zones of the abstract description in the generated diagram and to accept some unwanted empty intersections. In addition to the semantic goals, we state selected visual goals we aim to achieve. Our Euler diagrams should contain all elements, sets and their relations in a static visualization. Additional information can be optionally displayed using interactive user interaction. It should adapt to different sizes of elements. Additionally, we would like to include the set labels in the diagram and automatically position them without overlap. While researching Euler diagrams, we came across this human-made rectangular Euler diagram on Wikipedia showing the relation of different supranational European bodies. This rectangular layout is on the one hand very compact, while on the other hand it is adaptable to different sizes of elements. As input, we provide a table to our method that indicates which elements belong to each set. The table's first row represents the set names. The leftmost column represents the elements. A 1 in the table indicates whether an element is included in a set. In the first step, we combine all elements belonging to the same sets into element groups. We arrange the elements identified in the previous step belonging to the same sets into element groups. The elements should be combined in a preferably square bounding rectangle. We use an heuristic rectangle packing method to combine the elements into an element group. Therefore, we define a bounding rectangle for each element and combine these bounding rectangles into an element group. To reduce the complexity of the Euler diagram layout, we only arrange the element groups and move individual elements accordingly. Each element group contains at least one colored dot. These act as a double encoding and indicate in which sets all elements of an element group are contained. This also allows us to see in how many sets an element is included in. In this step, we define the constraints to arrange the previously generated element groups using a mixed integer linear program. To faithfully represent the relation of elements to sets, the inclusion of elements in sets and the exclusion must be modeled. To generate a visually pleasing diagrams, we formulate a list of constraints that should be fulfilled while a layout of the element groups is found. Constraints H1 and H2 express the inclusion and exclusion of element groups in sets. To avoid concurrent parallel edges of sets, we use constraint H3 to always keep a minimal distance between parallel edges. Constraint H4 places all sets in a bounding rectangle, which will be used in the next step to achieve an overall compact layout. Using constraint H5, we avoid overlaps of set names among each other and with elements. Constraint H6 reduces the number of empty intersections by prohibiting the intersection of sets with no common element groups. Constraint H7 models the subset property also visually in our diagrams. The constraints defined in the previous step ensure an insofar correct layout that all inclusions and exclusions have to be fulfilled. But this layout might not be necessarily compact. To generate a compact layout, we would like to minimize the area of the rectangular Euler diagram. We aim to minimize the area of all individual sets represented by rectangles. To enforce the overall compactness of the layout, we would like to minimize the area of the bounding rectangle encompassing all rectangles representing sets. As minimizing the areas would lead to a non-linear objective function, we chose to instead minimize the sum of the perimeters of all rectangles representing sets and the perimeter of the bounding rectangle. The sum of these perimeters is our final objective function we minimize. Regular shapes like circles and rectangles cannot generate diagrams for all set systems. Circles can, for example, only visualize Venn diagrams of up to 3 sets. Rectangles are able to generate Venn diagrams of up to 4 sets. To determine if a given dataset can be represented by one rectangular Euler diagram, we try to find an initial feasible solution for our mixed integer linear program for the full dataset. If we do not find a feasible solution within 50 seconds, we split the dataset in parts and try to find a solution for each subdataset individually. In the splitting step, sets are duplicated and element groups are distributed among the independent subdiagrams. As a baseline splitting strategy, we randomly split the dataset in multiple subdatasets. This led to Euler diagrams with many empty intersections. Therefore, we introduced a clustering-based splitting strategy. A short comparison of the results of both strategies can be found in our paper. For the cluster-based splitting strategy, we assign a binary vector to each element group, indicating in which sets it is contained in. The element group's binary vectors are clustered using the k-medius clustering with the Jacquard matrix. This is the final rectangular Euler diagram split in 2 subdiagrams. In both subdiagrams, the same color palette is used for the sets. Using our interactive web-based tool, users can interactively highlight the connection of split sets. In this example, hovering the mouse over the set horned shows a connecting line between the sets in both subdiagrams. We randomly assign colors from the Tableau color palette to rectangles representing sets. This can cause edges of similarly colored rectangles to be parallel and close together. To increase the distinctiveness of the colors, we adapted the automatic coloring technique Paetzold proposed by Liu et al. To suggest colors for our diagrams. Both color schemes are available for selection in our web-based tool. In a direct side-by-side comparison of the human-made and our fully automatically generated diagram, it is noticeable that the human-made diagram is more compact than ours. This is in part due to the fact that our method always places a set label in the upper left corner of a rectangle, and the elements are pre-arranged in element groups whose shape is not adaptable by the mixed integer linear program optimization. My co-author Rebecca will now introduce our online visualization tool.
This is the RectEuler tool interface. On the top, you can select the dataset you want to view. All the datasets of the paper are available. Let's, for instance, look at the Harry Potter dataset. The middle shows the Euler diagram. Each set is represented as a colored rectangle, and each element group is outlined with a black rectangle. Colored dots inside each element group show which sets this element group belongs to. We also offer some basic user interaction. You can pan by dragging the left mouse, zoom with the scroll wheel, and hover over some elements. Hovering over set name shows all element groups that belong to that specific set. All others will fade into transparency. Hovering over an element group shows all sets that this group belongs to. Hovering a colored dot shows a tooltip of the set name of that color. The color palette switch toggles the color between a random assignment of the tableau 20 colors and the automatically generated colors by Paetzold. If the user is not satisfied with an automatically generated color assignment of a set, he can click on the set name to open a color wheel, and this allows to freely change the color of the set, and the change is immediately represented in the visualization. On the bottom left, below the diagram, you can see the optimization timeline. Each bar represents one preliminary result, with the rightmost being our final diagram. You can click on each bar to see the respective diagram. If you want to see the evolution of the optimization, you can click through different steps of the evolution. Now, let's look at a more complex example, like the animals dataset. Some datasets cannot be drawn using a single diagram and are instead split into multiple sublayouts. In this case, it is possible to choose between two versions, either the splitting strategy random or the clustering split. If a diagram is not split, no choice of splitting strategy exists. We offer the possibility to step through the individual evolutions per sublayout. Additionally, statistics about the automatically generated Euler diagram, like the total runtime, including all time spent on individual solutions, are shown. The overall statistics match the number of sets, zones, and elements present in the formal description of the dataset to the actually realized values in the generated diagram. Representing the formal abstract description as a concrete Euler diagram visualization introduces visual artifacts like empty zones that are only present in the visualization but not in the abstract description. To analyze the occurrence of these empty intersections, we use stacked bar charts. Each bar represents an intersection depth, so the number of overlapping sets in an area. It is split in up to 3 different types: red, indicates regions in the diagram that are not present in the abstract description. Yellow signifies duplicated regions, for example, disconnected areas that share the same overlapping sets. And green regions have a one-to-one correspondence to the abstract description. The stacked bar chart on the left only applies to the currently selected sublayout, whereas the one on the right is aggregated over all sublayouts. By hovering over a segment of the bar chart, the corresponding regions in the diagrams are highlighted. By toggling the number of intersections and the area of intersection switch, the value of the bar chart can be changed to show the area distribution among the three groups in contrast to the number of intersections per depth. These overlays can be superimposed permanently using the Enable Overlay switch. As we split the dataset, multiple rectangles may represent one set. To remove clutter, the rectangles of a set are connected on demand when hovering a set's label. This allows readers to easily see all elements that belong to a set by keeping the visualization simple.
While our method is capable of generating clear rectangular Euler diagrams for a wide variety of datasets, it also has its limitations. As it introduces empty unwanted intersections, it is not well matched. Additionally, it is not well formed as zones might get disconnected. If the dataset is not representable by a single rectangular Euler diagram, sets are duplicated. As future work, the splitting heuristic of our method could be improved to avoid unnecessary splits and reduce the number of duplicated sets. Our method generates diagrams containing at least all zones in the abstract description. It could be used as a basis for local optimization, allowing for an example a more flexible placement of the set labels and elements. Additionally, local optimization could be used to reduce the number of disconnected zones. Thank you for your attention. You can try out our online demo at rectviz.de.